Rates of change. The average rate of change is the change in the function value divided by the change in the input value. In other words, you could think of the rate of change as the slope. If you remember, the slope is the change in y, that is the output value, divided by the change in x, and that is your input value. An example of the average rate of change is a trip that started at 10 a.m. and ended at 1 p.m., where the odometer in your car read 12,400 at the beginning and 12,580 at the end of the trip. So if you look at the output, or if you subtract 12,580 and 12,400, that will result to 180 miles. And the time elapsed from 10 a.m. to 1 p.m. is 4 hours. So this trip of 180 miles took 4 hours. And so we say that the average rate during the trip is 180 miles divided by 4 hours, and that is 45 miles per hour. In this example, the average rate is computed by taking the total distance traveled divided by the total time. And what we got is 180 miles for the total distance traveled and 4 hours for the total time traveled. Dividing that, you get 45 miles per hour. Now, the average rates of change in functions are found using similar computations. For instance, for y equal to f of x, the average rate of change from point x equals a to point x equals a plus h is given by this formula here. You have f of a plus h minus f of a. That is the change in your y values, or f of x. And the denominator is the change in x. It's a plus h minus a plus h minus a. This is the change in x. And simplifying this, we have f of a plus h minus f of a. This is the difference in the y values evaluated at these points, divided by h. H is the distance from point A to point A plus h. Now, to illustrate this, let us consider the following example. We are given here the function f of x equal to x squared plus 4x plus 5, and we want to find the average rate of change of the function f of x with respect to x as x changes from -2 to 3. Now, the average rate of change of f can be computed by taking the average in the y values divided by the average in the x values. So to compute that, we are just going to evaluate our function here at 3 first, and then subtract the value of the function evaluated at this point, -2. And then divide this by the change in x, so 3 minus -2. Now let's evaluate the function at 3. To do that, we will replace x here by 3. So you have 3 squared minus 4, plus 4 times 3 plus 5. Now 3 squared is 9, plus 4 times 3 is 12. That is equal to 21, plus 5 is 26. And then f of -2 is -2 squared plus 4 times -2 plus 5. -2 squared is 4, plus 4 times negative 2 is negative 8. So 4 minus 8 is negative 4, plus 5 is 1. So thus we have 26. So that's f of 3, and f of negative 2 is 1, minus 1, divided by 3 minus negative 2 is positive 5. 26 minus 1 is 25, divided by 5. That gives us 5. So 5 is the average rate of change of f of x with respect to x, as x changes from negative 2 to 3. Consider this example. A company manufactures plastic planter boxes. The revenue in dollars generated from selling X of these boxes is given by the function here. R of X, the revenue function, is equal to 20X minus 0.02 X squared whenever X is between 0 and 1,000. Find the change in revenue if production changes from 100 planters to 400 planters. Now the graph of the revenue function is given here, and we are to find the change in revenue if production changes from 100 planters to 400. So from 100 to 400. Now we know that the change in revenue, or the average rate of change, is just the slope of the line connecting these 2 points here. The average is just a change in y over the change in x. So the change in revenue, we'll call that AR over AX, is equal to, you just have to subtract the y values. So at x equals 400, you have R of 400 is 4,800. So you have, I'll write down the formula, R of 400, that's the y value when x is 400, minus R of 100 divided by 400 minus 100. Now R of 400 is 4,800 and R of 100 is 1,800 divided by 400 minus 100 is 300. Now 4,800 minus 1,800 is 3,000. 3,000 divided by 300 is equal to 10. Now this implies that the average rate of change in revenue if production changes from 100 to 400 planters is $10 per box. Consider another example. A small steel ball dropped from a tower will fall a distance of y feet in x seconds. This is approximated by the formula y equal to f of x equals 16x squared. The figure here shows the position of the ball on a coordinate line with positive direction down. Now, this is the position of the ball when at the end of 1 second, and that is equal to 16 feet from the original position. And at the end of 2 seconds, it is 64 feet. And at the end of 3 seconds, it is 144 feet from the original position. And now we want to find the average velocity from x equals 2 seconds to x equals 3 seconds. This can be obtained by finding the change in the position, the change in y, over the change in x, the change in our time. The change in the position at x equals 3 seconds. So that's f of 3 minus the position at 2 seconds, f of 2, divided by 3 minus 2. Now, referring to the figure here, at x equals, or at 2 seconds, the position is 64 feet, and at 3 seconds, the position is 144 feet. And so we plug that into the equation here. F of 3 is 144 minus f of 2 is 64. And 3 minus 2 is just equal to 1. Now, 144 minus 64 is equal to 80 divided by 1. So that is just 80 feet per second. That is the average velocity from 2 seconds to 3 seconds. Next, we want to find a general expression for the average velocity at x equals 2 seconds. Remember, our function is given by 16x squared. Now, the general expression, to get the general expression for the average rate of change, we follow the formula f of x plus h minus f of x divided by h. So our x here is 2 seconds. So we do f of 2 plus h minus f of 2 divided by h. So to evaluate this, we just replace the x here by 2 plus h. So we have, so on the side here, let us get the expression for f of 2 plus h. So we have 16 times 2 plus h squared. And then we simplify this. We have 16. Now we expand 2 plus h squared. That is 4 plus 4h plus h squared. And then you distribute 16. So you have 16 times 4, which is equal to 64, plus 64h plus h squared. Now this would be the expression that we're going to use to replace this. So we have 64 plus 64h plus h squared, quantity, that's for f of 2 plus h. And f of 2 is equal to 64 from our previous result, or from the graph, divided by h. Now 64 here cancels out. If 64 cancels out, we only have 64h plus h squared over h. Now h is actually a common factor. So we can factor out h in the numerator and then cancel that with the h in the denominator. Or you could just divide each term here by h. And this will result to 64 plus h. And so the general expression for the average velocity is given by 64 plus h. Now letter C, find the limit of the general expression you found in h as h approaches to 0. So you take the limit as h approaches 0 of 64h plus h. And this is equal to, evaluating this limit here, you just plug in 0 to h here. This is equal to 64. Now we have a special terminology for our last result. We call that the instantaneous rate of change at x equals 2. So in general, for y equals f of x, The instantaneous rate of change at x equals a is given by the limit of the average rate of change of f as h approaches to 0, provided that the limit exists. Consider the example. The position in feet of a moving object along a straight line is given by s of t equal to 2t squared minus 5t plus 40, where t is the time in seconds. Find the average velocity of the object from 2 seconds to 4 seconds, and then find the instantaneous velocity at 4 seconds. Now, the average velocity may be computed by finding the change in s at 4 and 2. So s of 4 minus s of 2 divided by the change in time, 4 minus 2. Now, to get s of 4, you just replace t here by 4. So you plug into your calculator, replace t by 4. You have 2 times 4 squared, that's 16, minus 5 times 4, that's 20. 32 minus 20 plus 40 gives you 52. Minus s of 2, replace t here by 2. So s of 2 is equal to 38. Divided by 4 minus 2, which is 2. Now 52 minus 38, 52 minus 38 is equal to 14, divided by 2 is 7. So the average velocity of the object from 2 seconds to 4 seconds is 7. Next, let's compute for the instantaneous velocity. The instantaneous velocity can be computed by finding the limit as h approaches 0 of the average velocity at 4. So s of 4 plus h minus s of 4 divided by h. So to evaluate this, we will have to first obtain the expression for s of 4 plus h. On this side, let us obtain s of 4 plus h. We obtain the expression by replacing t here by 4 plus h. So we have 2 times 4 plus h squared minus 5 times 4 plus h plus 40. And then we expand this. We have 2 times, so expanding this, we have, if you square the first term, that is 16, plus double the product of the two terms, that's 8h, plus square the last term, h squared. Minus, now you distribute -5 to each term in the parentheses here. So you have minus 20 minus 5h plus 40. Next, you distribute 2 to each term in the parentheses. So you have 2 times 16, which is equal to 32, plus 2 times 8, which is 16h, plus 2h squared. Then you copy minus 20 minus 5h plus 40. Then you combine similar terms. So let's begin with the leading term, 2h squared. So you have 2h squared. And then you have 16, positive 16 minus 5h is 11h. And 32 minus 20 plus 40 gives us 52. Then next, we plug in our result here in here. So let's now evaluate the limit. So we will replace this expression here by this. We have 2h squared plus 11h plus 52 minus, now s of 4, we have previously calculated that to be equal to 52. So minus 52 divided by h, and then we take the limit as h approaches 0. Now 52 here will cancel with 52 here, and then the resulting expression will have h as a common factor. So you can also cancel h to each term here, or you could factor it out. So you have h times 2h plus 11 divided by h, limit as h approaches 0. Now you can cancel h. So then you're left with 2h plus 11. And then now you take the limit as h approaches 0. So as h approaches 0, this term here will just approach to 0. So the limit is equal to 11. So we say that the instantaneous velocity at t equals 4 is 11 feet per second.